Okay, so when we say pluck a guitar string or hit a piano key or play an oboe or a trumpet or whatever, like what physically is going on, right? What is the sound that we're actually hearing? And why do different instruments sound different, even though they're playing the same note, you know? And for that matter, you might wonder, how is it that we're able to store the sound of an entire symphony or an entire band playing at the same time, just in like the up and down grooves of one of those old vinyl records, or maybe even more mysteriously in just the zeros and ones carved onto a CD or stored in hard drives of our computers? So understanding those kind of questions is going to be the goal of this section 10.2. And we'll start out with section 10.2.1, vibrations, oscillations, and harmonics. Vibrations, oscillations, and harmonics. So I want to start out by thinking about a vibrating string, right? And one of the first things to notice, so, let's just say I've got a string stretched in between 2 points under a certain amount of tension. So the string is under a certain amount of tension. And so if I zoom in on like the little, tiny bits composing this string, the string looks like some cylinder. Each of these little parts of the cylinder feels like it's being pulled in 2 directions from the tension running all along the line. But the forces from these tensions cancel out, and so nothing actually accelerates. There's no net force on any part of this string. But if we say go to pluck this string, so we pull it into a curve, the situation is different. So if I zoom in now on this part, what it looks like is a curved tube. And now, what does every small segment of this stretched string or piece of wire look like in terms of the forces it's experiencing? Well, this little segment, which used to be flat, is now curved, and there are these tensions that are pulling on it from both sides as it feels the tension in this wire. But you'll notice now that the directions that these tensions are pointing don't cancel out to zero. And that means that there's a net downward force in this case. And that means that if we let go of the string is going to want to, it's going to start accelerating downward. It's going to get to a maximum velocity when it's straight. Its inertia is going to carry it into the opposite curvature. And then, as it bends into the opposite curvature, it's going to slow down. These net forces are now going to be pointing, upward, and the string is going to vibrate back and forth. In other words, a stretched string under tension is another one of these harmonic oscillators. Okay? And the simplest mode of oscillation is what we've just drawn. It's called the fundamental vibrational mode. And if I get a little animation, it looks kind of like this. The string goes back and forth from its initial position to the opposite. Here I've only had it do half of a loop, but it would go like this. Back and forth, right? And that mode of oscillation has some particular characteristic frequency, just like any oscillator would have. So what is the frequency of a vibrating string? Well, the frequency of a vibrating string, what we might call the fundamental frequency, which is the frequency of this shape that I've just drawn going back and forth, and you'll see why I'm specifying fundamental in just a moment, that frequency is given by the following expression. We've got 1 divided by 2 times the overall length of the string, divided by, or multiplied by the square root of the tension in the string, divided by the linear mass density. Linear mass density. I've tried to draw the Greek letter mu. And that's equal to the mass per unit length. So a string that has a certain thickness made out of a certain substance will weigh a certain number of kilograms per meter, for instance. And that kind of measurement is what I mean by this linear mass density. Linear because it's a measure of mass per length, not mass per volume, per unit length. Okay. And so dimensionally, you can kind of check that the dimensions of everything work out, right? So we have force, which is, for instance, in units like kilogram meter per second squared, divided by kilograms per meter. So all told, that's going to be, after taking the square root, meters per second divided by meters. So 1 over seconds, or hertz. Okay. Now, an important feature of vibrating strings is that actually they don't only have one natural frequency. So vibrating strings have many natural frequencies. And to keep track of them all, we often talk about them as harmonics. So the first harmonic is the same thing as the fundamental mode. So it's when the string looks like this, there's just like half of a wave. Why do I say half of a wave? Because a full wave would be up and then back to where it started and then down and back to where it started. But we don't see this half, so great. This would be the fundamental, also known as the first harmonic. The second harmonic is where we have both the up and the down part of the wave in here. So this kind of shape would be called the second harmonic. And if you like, this is what that mode of oscillation actually looks like. And you'll notice that it actually oscillates back and forth faster than this fundamental mode does, right? Faster than the fundamental mode does. And why is that? One of the pieces of nomenclature that go into these so-called standing waves, standing because the wave isn't actually traveling anywhere, it's just oscillating back and forth on a stationary spring, is that there are these nodes and antinodes. So let me say nodes here, and antinodes in this case here. So nodes are where the position of the string doesn't actually change. So in the fundamental mode, that's just where the string is fixed to its two ends, and that position always stays fixed. Antinodes are where the string moves the most over the course of one of its cycles. And so in these animations, you can see, for instance, the center of this curve moves farther than any other point over the course of this oscillation, and so that's an antinode. Okay. Well, this next harmonic mode, second harmonic mode, or you can just call it the second harmonic, you can see that it has not just the two nodes at the ends, but also a node right in the middle, and two antinodes, a third and 2/3 of the way through the string. You can see that in this animation here, where if you look right in the middle, over the course of the animation, it doesn't move at all. And then, over here and over here, you have these things oscillating the most. So in these higher harmonic modes of oscillation, it's as if you had a string which had an effectively smaller length. And so because the length gets smaller, the frequency of these higher order harmonics is higher. So they have a shorter length, a higher frequency, a concept that we'll see a few more times in the next sections. Now, we can keep going. If I draw a more complicated waveform stretched between here, you can figure out which harmonic it is if you want just by counting the number of nodes. So this has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 nodes. And so apparently this is the 11th harmonic mode, right? The pattern being that, the number of nodes minus 1 is like the order of the harmonic, right? And you could see I could have, drawn this picture crazier and crazier to fit more and more of these small little wavelengths in between the two ends of the string. And in fact, there really are just this, in principle, endless sequence of high order harmonics that a vibrating string can vibrate in. Okay. There's a few interesting things that we'll want to talk about in the context of this. First, the existence of these harmonic modes is why different instruments actually sound different, right? And it's because the same string can be simultaneously vibrating in more than one of these modes at the same time. And so, for instance, the easiest combination I could do might be to just add these two modes together. So I could have a string that was vibrating simultaneously in the fundamental and second harmonic mode, and it would look kind of like this. So if I just add these shapes together, and that's how these waves actually compose, you just directly add them together. So if I take this shape plus this shape at first, well, let me make sure these are both at the beginning, this shape plus this shape, you can see that now I have something that looks asymmetrical, right? And if I let this play forward in time, the way that it evolves is literally just the sum of, this movie playing together with this movie, right? Every particular instrument, every particular, type of string and the body connected to that string has some, different combination of these fundamental and harmonic modes of oscillation of the strings that are actually ringing out. And the particular mixture of modes that each different instrument produces is called the timbre of an instrument. So, in case you're curious, timbre, spelled like so, is the particular combination of modes that a given instrument sounds. When playing a note. Okay. When playing a note. And the idea here is that any particular vibration of a string can be made out of not just adding these different modes together, but adding them together with different amplitudes. So some particular sound might be, some large amount of fundamental plus some, tiny amount of third harmonic plus some incredibly minuscule amount of fifth harmonic, and so on, right? It could be any combination of both which modes are actually being oscillated and also the strength of each mode in that particular mixture, right? And so, for instance, here I've just picked a random mixture of different amplitudes of these different fundamental frequencies and harmonics to oscillate this string according to. And you can see that the actual way that the string distorts can be some pretty complicated shape. And the details of what shape the string will actually be vibrated according to depend on the material of the string, the way that it was plucked or bowed, if you're using a violin, for instance, the body of the instrument that the string is connected to, so on and so forth. And, sometimes those patterns of oscillations look like kind of just a random mess. Sometimes you can add things together in very special ratios to give you really interestingly well-defined shapes. So for instance, if you take a stretched string and you just pull it from the middle, that basically makes it look like a triangle instead of one of these smooth curves. You get a string that has a triangular shape. And that kind of triangular shape is a particular mixture of a bunch of, it turns out, odd-numbered harmonic modes. And so, for instance, this triangle, if I slide this animation over a little bit, this overall triangular shape is basically composed of the sum of a lot of these different fundamental and harmonic modes ringing together, oscillating together on the same string in different amplitudes. Okay. One of the things that I think is really quite cool is actually all of our computers these days have free access to recording software that lets us see the shape of these oscillations just on our computer screens. So for instance, if I pull up, this is the program Audacity, which I believe is a free recording software which is available both on Windows and on Macs. So let's use this program to look at the shape of the oscillating waves produced by a random stringed instrument. So let me start out by just hitting record here and then playing, I don't know, how about this one? Great. How lovely. So let me first just kind of get rid of all of that nonsense at the beginning. I'll use this just to make these waveforms just visually larger so that we can see them more easily. And then let's zoom in. So as we zoom in, and you can see the amount of time that's elapsed, you can see the shape of the vibrations that we were just listening to. And you can see that there's an overall dominant frequency with which the peaks of these waves come, from here to here to here to here to here, so on and so forth. But there's all these little extra wiggles that themselves, repeat with a certain periodicity on top of that fundamental frequency. So that fundamental frequency is what we call, the basic pitch of a note that we just listened to. But all of these extra pieces of the waveform is what makes, this guitar sound different from a violin, even when it's sounding the same note. You can also see visually what you heard with your ears. That is, as the note rang out, the kind of sound of that note changed over time. And that's because, this dominant frequency persists, but the rate at which each of these higher order harmonics fades away is different. And so if I just scroll forward in time, you can see the overall shape of the combination of waves changing until, towards the end, you have something that's almost just a simple pure tone, where you've lost all of those kind of rich harmonic overtones that the instrument was producing. And then at some point I touched a string by accident or something. Great. Great. Very good. So let me just get back on track here. Excellent. So this idea, for instance, of having a vibrating string is basically how stringed instruments work. And, one little complication is that, as we'll learn in just a second, sound is communicated through the air. And air is really good at getting out of the way of these vibrating little strings. And so a lot of the construction of the body of an instrument is designed to communicate the vibration of the string back and forth into oscillation of the body of the instrument itself. And that lets the body of the instrument create sound waves that travel more easily to our ears. Great. Okay, great. So that's section 10.2.1. 10.2.2 is other instruments. Other instruments. Right, so stringed instruments, as I said, kind of all work basically in this way. You use strings that have different thicknesses or that are under different amounts of tension so that you can tune each string to a different fundamental frequency. Right? And you can also alter the fundamental frequency of any given string by holding that string down against the instrument, or for instance against the guitar fret, right? That basically shortens the overall length of the string that's actually doing the oscillation, and by shortening the overall length, you increase the frequency of that fundamental pitch. Great. Most other musical instruments work not by creating a standing wave on a string, but by directly vibrating a column of air. That's what pipe organs do. It's also what every wind instrument is basically doing. So, a trumpet is like a tube of air wrapped in a bunch of coils with valves that can effectively shorten the total length of the tube. And when you blow into a trumpet, you're creating an oscillating pattern of air inside that tube, and the length of that tube, just like the length of the string, determines the fundamental pitch of these wind-based instruments. And just like strings, columns of air can have lots of different interesting harmonic modes on top of the fundamental mode. So that's how most other wind-based instruments work. And I would say the majority of instruments fall into one of three categories. They're either these string-based instruments or these wind-based instruments where you're vibrating a column of air instead of vibrating a string. So those are two of the most common types. This class is not going to be about musical theory, but I'll say a few words about how these fundamental frequencies relate to notes and pitches. So in, let's just say, most musical traditions, people, I'm just going to put in quotation mark, nice integer ratios of frequencies. So if you hear a pitch and then you hear another pitch whose frequency is twice as high, so a ratio of 2 to 1, those sound very harmonious to most people. And so, for instance, an octave in music is one of these ratios, is a ratio of 2 to 1 in frequencies. Okay. So in Western music, pitches are based on this note that's called A4 or middle A or concert A sometimes. And this is a note, whose pitch has been standardized, whose pitch is defined to be 440 hertz. Okay. So one octave above A4 is another note named A. So A5 has a pitch of 880 hertz. Okay. And A3, the A an octave below A4, has a pitch of 220 hertz. Okay. For any musical theorists in this class, I'm ignoring equal versus well temperament. There's some interesting mathematics that go on here. Another example, another really important example, is the ratio of 3 to 2. So this is called a fifth in music. So for instance, the note E5 has a pitch which is 3 over 2 times the pitch of A4. And so that would be 660 hertz. Okay. Sorry. Okay. The email never ends. And so on. Other important examples, for instance, the ratio 5 over 4, which is a third in music, is another kind of nice ratio of simple integers, and these kind of ratios of pitches are judged to be very harmonious. And this is not just something that's true of music in the Western tradition. These kind of nice ratios of frequencies of pitch relative to each other can be seen in all kinds of musical traditions. So for instance, here's an image of an extremely old stringed Chinese instrument, and you can see that there's these 7 strings of different thicknesses and tensions stretched so that they have some length. And there are these markings that are put so that instrumentalists can know where to push down on these strings to get different sounding notes. And if you measure the lengths of these strings, you'll see that these dots are all in nice, simple ratio positions. So if this whole length is just something that I'll call the length of one instrument, this dot is right in the middle, and this dot is a third of the way across, and this one is 3/5 of the way across, and so on and so forth. So almost every musical tradition in the world has this kind of feature where sounds that we think sound good together happen to be simple integer ratios of pitch frequencies. Okay. It turns out that these nice kind of even ratios of frequencies are so deeply ingrained in how we perceive things that it's also basically one of the reasons that we think most percussion instruments don't have specific pitches. If you look at the surface of a drum, for instance, when someone hits a drum, we kind of just perceive it as an atonal kind of thwap, or there's no pitch that we automatically associate with that. Well, the reason for that, the surface of a drum has a fundamental frequency that it oscillates according to, and it has these higher order harmonics as well. But surfaces, as opposed to linear objects like strings or columns of air, surfaces have harmonics, where the frequencies of the harmonics are not simple ratios or simple multiples of the frequency of the fundamental, right? So you'll notice that in these kind of simple versions of the harmonics on a string, you have your fundamental, you have something which is, has a length which is effectively half as long, or a third as long, or a fourth as long, And that means that the frequencies are like the fundamental frequency, twice the fundamental frequency, 3 times the fundamental frequency, so on and so forth. For surfaces, that's not the case. And so the harmonic frequencies of everything above the fundamental are just these weird kind of, random real numbers that depend on the detailed geometry of the surface and its size. So because of that, we tend to perceive, the sound of a drum as really very different than the sound of, a string or a wind instrument or something like that. Some of the exceptions are things where you build a percussion instrument by hitting objects that have particularly well-tuned resonant frequencies. So for instance, you take a xylophone, which is composed of a bunch of small wooden blocks, and those wooden blocks have been chosen. Their density has been chosen and the shape they've been carved into so that that wooden bar has a brief little, resonant frequency, which is easily identifiable. And, many objects have something like that. I think I used this soup ladle in a previous lecture. And, if I let this soup ladle ring out, the sound damps away pretty quickly, especially when I'm having trouble balancing it. But it does ring out a little bit for a little bit of time. And so, for instance, if we want, we can pull up and see what that actually looks like. I think it was basically this little bit here. So let me just make it a little bit bigger on the screen and then zoom in. And you can see that there is this overall frequency, which was the thing we heard kind of ringing and quickly dying away, with some of these, higher order harmonics on top of it that kind of ring out for a very little bit of time. Okay, so that's what instruments are doing. Instruments are, taking a string and letting it vibrate in different ways at different fundamental frequencies with certain combinations of harmonics on top of the fundamental frequencies. How do we actually hear that? What is actually communicated so that when a string is vibrating or the body of a violin is vibrating because the string is vibrating, we actually hear sound reaching our ears? What's actually moving? So sound, let's say in air. I'll talk about everything as if we're just thinking about sound in air, but sound can travel through any material, can travel through gases, liquids, solids, so on and so forth. Sound is a traveling wave. A traveling wave of basically compressed and rarefied or less dense air. Of compressed and rarefied air. Okay. And so if we want to look at an example of that, here might be a typical picture. So when there's a source of sound at some particular, let's just say frequency for now, you'll have this alternating pattern of denser regions of air and less dense regions of air as the sound travels across the room. So in this case, the sound is traveling from left to right, and the way that looks is, something like this, right? So these regions of compressed and decompressed parts of air kind of travel in a direction. Sound waves are sometimes called longitudinal waves because the direction in which things are changing, in this case getting more or less dense, is the same as the direction that the sound is actually moving. That's in contrast to waves on a string. And I don't have very many easy chords to work with. Here's a printer cable. I do not know how well this shows up on your screen. But if I send a pulse traveling from one end to the other, in this case, the direction of oscillation is, say, up and down, whereas it's moving from right to left. Right? And so waves on a string are sometimes called transverse waves because the direction of motion is transverse to the direction of propagation. Okay. Sound waves, longitudinal traveling waves. Longitudinal traveling waves. Great. So I just want to sketch something really quickly. So I kind of just showed this kind of pattern of like denser and less dense, and then less dense, and then denser air traveling to the right, and what I want to do is kind of make a plot of this, where on this y-axis here, I'm going to think about the density of the air, or equivalently, the pressure of the air. Okay, and this like pattern of denser or less dense air, or higher pressure, lower pressure air, is like oscillating about whatever the density of air in the room is, or whatever atmospheric pressure is, right? And what we see is that in this pattern of like dense, less dense, dense, less dense, you have this oscillation. In some ways, very similar to the pictures of oscillation that we had earlier. And I just want to point out that there's some nomenclature that goes along with this. The kind of total distance from the peak of one of these waves to the trough, or the difference in density between the densest part and the least dense part of this traveling wave, that's called the amplitude. The distance from one peak to the next, or really any part of a wave to an equivalent part of the wave, that's called the wavelength. So here lambda equals the wavelength. These waves have a frequency, just like they have a wavelength frequency. And they have both a speed and a direction. But for now, let me focus on just the speed of these waves. Okay. Okay, so when sound is produced, we have this basically alternating pattern of high and low density regions traveling at some speed in some direction. And there's a physical distance that separates two regions of high density, or equivalently two regions of low density. That's the wavelength. And the oscillations are happening with some frequency. So what mathematical equation relates all of these things? It's the following. It's that the wave speed is equal to the wavelength multiplied by the frequency. Or in symbols, we could say the speed is equal to this Greek letter lambda times the frequency f. Okay, so does that mean that if we play a note that has a lower frequency, it's going to travel at a different speed? So if we decrease frequency, does the speed change? No, it does not. The speed of sound through anything, through a gas, through a liquid, through a solid, is determined by the properties of the thing sound is moving through, not the properties of the oscillations itself. So the speed of sound is set by the material. Okay. Is set by the material. So for instance, the speed of sound in like air at room temperature is about 345, I think, meters per second. Or the speed of sound in like seawater is something like 1500 meters per second. Okay. So what this equation is telling us is not, as you change frequency, for instance, the speed changes. It's that the speed is physically fixed by the properties of the material sound is moving through. And so the product of wavelength and frequency has to stay constant. So if you have a surface which is, oscillating back and forth with some frequency, that's going to generate sound waves whose wavelength is set by, the speed of sound divided by this frequency. And then if you double the frequency of oscillation of that surface, you'll half the wavelength, so that, the speed of sound, this wave speed of sound, stays the same. So this wave speed of sound stays the same. I want to point out that by thinking of sound as a traveling wave that moves with some velocity, that actually explains something that's called the Doppler shift, right? I don't know if you've ever listened, say, to a car as it like speeds past you, but it sounds like, or something like that, right? When it's coming towards you, there's kind of a higher pitch. And then when it's receding away from you, it sounds like it's emitting a lower pitch. What's actually going on is that the car is emitting a certain sound with a certain frequency, and we're standing still. So because there's relative motion of the source and of the observer, the rate at which our ear hears the peaks and troughs of this dense and less dense sound. Let me maybe play this animation again. You know, if you imagine us standing over here, I guess I can do something like this. You know, if you imagine us standing over here, we have these compressions and rarefications of air moving past our eardrums, which is how our brain detects sound, at some particular frequency. We detect a certain number of these peaks of dense air per second, for instance. Well, now, if we're moving towards this source of traveling waves, our ear will encounter these crests of the waves more frequently. And that will be as if we're hearing a higher frequency source. And in contrast, when we're running not in the same direction, but moving away from it, or equivalently, when we're standing still and a car is moving away from us, we run into fewer peaks per second than if the source and the observer were standing still. So that's called the Doppler shift. Doppler shift. Quite fun. Okay, so that's kind of our little introduction into the physics of sound and the physics of music. And honestly, one could teach an entire course on the physics of music. I think it's a fascinating subject, and we've barely scratched the surface. If nothing else, I encourage you to just like play around with some of these, tools. The fact that high quality electronic processing is now cheaply available to basically all of us means that you can really see with your eyes these kind of physical concepts that are otherwise, hard to detect. If you just, take a stringed instrument, and play one of these strings, well, our eyes cannot quickly enough make out the shape of the string at every instant, and you basically just see a blur moving back and forth. But by taking slow motion videos or looking at some of these audio softwares, you can actually see the shape of the oscillations that these instruments are producing. I think that's quite cool. All right, so this kind of physics of vibrating strings is kind of the second type of mechanical wave that we'll see in this chapter. We'll meet the last one, water waves, in the next section. And then the next whole chapter will be devoted to an extremely special type of wave, electromagnetic waves.